Okay, so good morning. Yesterday evening, if you remember, we stopped at this point where we were discussing about the stress distribution in a cross-Lampadel loaded outer plane with bending. And we said that basically the easiest way, or if you want what is called the simplified method, which is more than enough when we go to do the ultimate limit state check of our paddle, is basically based on the assumption of just consider the layers of plants running parallel to the direction of the stress induced by the bending moment. So the idea is that if you have 5 layers, we just keep into consideration the 3 layers that are that have the fibers oriented parallel to the direction of the stresses induced by the bending moment. As far as the other 2 layers are concerned, we can just ignore them. So basically, we consider a cross-section made only from 3 layers in this direction. Of course, the other 2 layers in the other direction. We just assume the Young modulus. We just basically consider the 2 intermediate layers as if they were with the Young modulus equal to 0, basically. Okay? This means that we can get in the end this kind of linear distribution of stresses. We can use the Navier formula, exactly the way that you know. Here in this formula you can find actually the bending stiffness, but of course this is because if you want to do a bit more precise, you could also consider the Young modulus of the intermediate layer, which is different from 0. You should consider the Young modulus of wood perpendicular to the grain. And then in this case, you would have to basically homogenize using what we call the transform section method. But again, since the differences are really negligible, I would say just ignore the intermediate layers, so the ones that are oriented perpendicular to the grain, and just use the normal Navier formula, where here you can replace KCLT with the first moment of inertia. And there, of course, if you put here the first moment of area, then here you ignore the E. Okay, so you just use the normal Navier formulation to calculate the sigma. Now, if you want, as we said before, you want to check a panel subjected to a certain bending moment, so you calculate the max stress with the formula we say M divided by first moment of area times Y max. Then of course we need to compare this design stress with a strength. Now, the strength of a cross-Lampadel, the design strength of the cross-Lampadel, FMCLTE, so FMCLTE, so this is the design strength of a cross-Lampadel in bending. Okay? As usual, this is given by K mod times FMCLTK divided by gamma n, the normal safety form of verification that we know, where FMCLTK is the characteristic bending strength of a cross-Lampadel. Now I have to say that for the time being, if you look into the Eurocode file, you won't find any information about CLT, because CLT is a relatively new product, and when the Eurocode file was published, it was not used at the time, it was used very seldom. So now in the Eurocode file, and also in the Italian regulation, I would say, also in the CNR, you won't find anything about CLT. However, the Eurocode 5 is under revision, and there will be a new generation of Eurocode 5 which will be published in maybe 1 year, even less, and will become effective in 2022, 2023, so we're still at least 4 years behind the final date when the new regulation, the new version will become effective. So, as I said, in this new version that we are now working on at the European level, there will be 1 chapter just dealing with CLT. So there will be a new chapter with all the information that we need to do the design with CLT. So, you can see here a proposal. As I said before, if you remember, I told you that in Graz, in Austria. There is a technical university, there is a colleague called Gerhard Schikofer who spent all his professional life working on CRT. And so they suggested some relationship like this, for example. So they say if you have a CRT panel, you want to calculate the bending strength of this CRT panel, you need to relate the bending strength of the CRT panel to the tensile strength of the board. More or less like with Lula. With Lula, we said we have several laminations. So the bending strength of the glula as a material in some way will depend on the tensile strength of the single planet. Same thing here. So the C characteristic bending strength of cross-slab will depend, you see here, on this quantity Ft0Lk, which means characteristic tensile strength of the plane parallel to the brain. So as we said before, if this is my cross-slab cross-section, here we have some lamination, some boards. Here we have the distribution of stresses. So, who is going to govern here the bending strength of the cross-slab panel is mostly the tensile strength of this lamination here. Strictly speaking, this lamination is subjected to combined bending and tension. It's not a pure bending. Sorry, it's not. It's not a pure bending. It's not a pure bending. Neither a pure tension. Because you see here, you have a distribution like this of stresses. This means that it is pure tension plus bending, pure bending, okay? On the lamination. But of course, who governs more is more important than tensile strength. So in the end, they derive this kind of empirical relationship correlating the tensile strength parallel to the grain of the board to the bending strength of the whole body. So they give several tests. So this proposal is here, where you can see a CRT has a recommended value of 3, based on some test, depends on coefficient variation, lamination, and so on. And then this Ft0Lk is to the power 0.8. Again, empirical relationship. So in the end, for each type of stress, we can get a relationship like this, where we can correlate the property, the mechanical property of cross-slab to the mechanical property of the lamination making the cross-slab. Okay? If we will see later on, there is now a table, a proposal into the new Euro 5 of a table. I can actually show you just some images, just to understand what I'm talking about. A table like this, where, for example, characteristic value of strength and stiffness and density for cross-laminated timber comprising timber layers derived from the property of the timber lamination. So you are designing a cross-slab panel. This cross-slab panel is subjected to axial force, for example compression, because you're using a cross-slab panel for a wall. So you're interested in the compression strength parallel to the edge for this panel. Well, how can you calculate this? You go here, compression strength, in plane or perpendicular to the plane? In plane, for example, because we are studying the wall like this. 3 layers, suppose we have 3 layers. So you have a situation like this. Cross-slab wall subjected to an axial force. How can you do the check, the verification? We said yesterday you have to consider as a resisting cross-section only the layers that are oriented parallel to the stresses. Stresses induced here will be stresses like this. So our resisting cross-section will be only this. Okay? I calculate the sigma compression will be N divided by the effective area. Effective area, if we call this with T, and this one with B, Usually B is 1 meter, so we just calculate per meter. So will be sigma C equal to N divided by 2T times B. Because we have only 2 layers existing, okay? And then we need to compare the sigma C. So sigma C must be compared with a compression strength of the cross-lamp panel parallel in this direction here. So parallel to the direction of the force. Now we go here, compression strength. Is compression in plane or is it perpendicular to the plane? First question for you. Is this compression in plane, in the plane of the panel, or is perpendicular to the plane? In plane. Because perpendicular to the plane would be something like this. Okay? So this is compression in plane. So, first line, compression in plane, FC XK, FC YK. Why do I have to value here? Why there are two values there? FC XK, so what does it mean to have two values? FC XK and FC YK, what do you think? Which one is FX, FXK, what is written there? FC XK and FC YK?
It's parallel to the.
Okay, so this could be, let's say FC XK, and the other one? Because also the other one is parallel to the plane. Sorry, also the other one is in plane. So which one would be the other one? No, because the axis is different. So this is x. So if this is x, which one is y? If this is x, I could have either this or this one. Which one is y? What do you think? The last would be, I don't remember which one was the last. This one. This one. Yes, because the other one is the axis would that be in plane or perpendicular to the plane? This would be perpendicular to the out of plane. So in plane is this, so this is x and this is y. So this means that if I have an axial force acting in this way, then I will have to use FCYK. And the resisting cross section here will be which one? In this direction. Which one will be the resisting cross section? Yes, which means, again, like we done yesterday, would be only this. Okay? So it would be like so this should be a sigma Cx, the other one would be sigma Cy equal and divided by Td, only one layer, less than or equal to, so this is Fcxk, sorry, this should be Fcxd, this is sigma x, and this would be, no, I don't have any more room, obviously. Sigma Cyk, sorry, sigma Cy equal n over Td less than Fcyd. Okay? So Fcyd will be K mod times Fcyk divided by gamma n. And this one, same thing. Okay? Now, who gives us Fcyk? Fcyk is taken from this table. Also, Fcxk, which will be this relation, is taken from this table. Okay? The value, you see here, value 3ft0nk to the power of 0.8. So I correlate basically the compression strength of the panel again to the tensile strength of the single board parallel to the plane. Okay? So with this panel, of course, if I know the strength class of the timber, and of course I have to know the strength class of the timber, because all the plants, as we said from the very beginning, shall be classified. So for each piece of timber, for each plant that I use to do the crossland panel, I need to know the strength. So I need to know whether this is a T10, T12, so the tensile strength of the plant. Okay? It's clear? So I know the tensile strength of the plant, I take the FC0LK from the classification table that we saw several weeks ago, and I insert this into this formula, and I get the property, the mechanical property that I need to calculate the strength of the panel. Okay? So as you can see, in the new version of the Eurocode 5, there will be this table. Not in the version that we have now, there is nothing, but of course, if we have to calculate now a crossland panel, we can't really wait for another 3 more years, because, as I said yesterday, crossland panels are very much used right now, and so in this presentation you will find this table. You can use this table to do your design. What we need also, as you can see, is K-mod, the modification factor for strength and moisture property. Also, this is not in the Eurocode 5. So, also for this, we need to use this table here. So, in the new version of the Eurocode 5, there will be a table like this, with a new line, cross-laminated timber, Service class 1 or 2, 06, 07, 08, 09, 1.1. So, you have the K-mod also here. Just be aware that, as you can see, there is no serving class number 3, only 1 and 2. Why there is no serving class number 3? Because the idea is that a crossland panel should never be used in serving class 3. So it should never be exposed directly to the rain. Why that? Because you have a number of timber boards glued together, then you may have lots of problems. Then, if you need to calculate, for example, for a floor, the deflection, you have also here the KF, which is the creep coefficient, 7 class 1.8, 7 class 2, 1. The creep coefficient, as you can see, is slightly higher than the creep coefficient of Lula. So for Lula would have been 0.6 and 0.8, and here is 0.8 and 1. So we need to consider these values here. The partial safety factor, gamma n, is like the one for Lula. So the recommended value is 1.25, like the one for Lula. Also, this paragraph, which is taken from the new version of the Eurocode 5, as you can see here, they said that unless the strength and stiffness properties are explicitly related to the gross cross-section of the cross-laminated timber, they are related to the effective cross-section layer with grain direction parallel to the respective stress. So what we said yesterday, they said basically we don't need to take into account the layers perpendicular to the grain multiplied by the Young modulus perpendicular to the grain. We can just ignore that, like we've done yesterday. So we just consider what we call the effective, what is written here, effective cross-section. Effective cross-section is the gross cross-section less the layers that are loaded with very low stresses. So less the layers that are perpendicular to the grain. Okay? So here, as I said before, in this table you have all the properties that you need. There is also a drawing like this showing the orientation of all the different axes. So if, for example, if you are not sure where is the X or Y and Z and so on, you refer to this drawing here. Where you see, for example, X, Y. So X and Y are axes in plane, while instead Z is the out of plane axis. And then you see we have axial forces, so two axial forces along X and along Y, two out plane bending moment, MXX and MYY. Then we have the torque bending moment, MYX and MXY. We have the axial force, well, the axial force we already said, and Y and X, the axial forces. And then you have the shear. You may have in-plane shear, or you may have out-of-plane shear. And then, of course, you may have out-of-plane compression. So for all of these properties, there is a formula to calculate what we call the characteristic resisting property. So now what we still need to deal with is shear. So we lost a bit back with this presentation, and we talk about out-of-plane shear. So how can we calculate the shear stress distribution due to out-of-plane? Again, like for bending moment, we use the Juravsky, in this case, formula, so the one that you learn in mechanics of structures, by considering only the effective cross-section. So again, we need to consider which layers of boards will resist the bending induced by the shear. So again, let's do it with we can start with a 3-layer, even though that the 5 is more relevant, but okay, let's start with a 3-layer, like yesterday. Okay, so this is my cross-section. Suppose this cross-section is loaded in shear, out-of-plane shear. This is our T. Basically, the idea is that this shear is associated to a bending moment, to an out-of-plane bending moment. So, which layer will be stressed with the sigma oriented parallel to the grain? In this case, so we're talking about the shear. This shear comes from a bending moment, right? Because we don't. Can we have a shear without a bending moment? No. Can we have bending moment without shear? I think we've already discussed. Maybe I'm going to discuss with the other class of the theory. So we cannot have shear without, what we said before, we cannot have shear without bending moment. Can we have bending moment without shear? Yes or no? Yes? In which case? Exactly. Which case? The practical case could be, for example, if you have a beam, 2 supports, you load the beam on the overhand. Something like this. In this case, this inner part, here you have only bending moment and no shear. Okay, but anyway, if we have shear, what you told me before, if we have shear, for sure there is a bending moment, because you cannot have shear without bending moment. So, my question is, we have this shear acting this cross section. The bending moment associated with this shear will induce what kind of stresses in the cross section? So if we load this layer or the intermediate layer, of course there might be maybe the question I gave you before could be a bit doubt, but of course in one cross section you may have only shear and not bending moment. One cross section. If you think about the simply supported beam, on the support you have only shear, and in no bending moment. In the center, at mid-span, you have only bending moment and no shear. But in the structure itself, it's not possible to have a piece of structure, section of, let's say, yes, a length of structure with, for example, only shear, not bending moment. In a cross-section, yes, but not in the length. Okay? Now, going back to my question, you have a shear here, acting this cross-section. We need to understand which layers are effective for the shear, for the tensile, for the shear stresses induced by the shear. To understand this, we need to understand which layer will be effective for the bending moment induced by the shear. Now, this shear here, what kind of bending moment may induce? So, the bending moment induced by this shear will stress which layer? This is the question that I'm asking to you, which is easier of what it seems. So, any idea? So the two outer layers. So first of all, which will be the bending moment here? There will be a bending moment, something like this, or in the other direction. We don't know. But for sure, this bending moment is an out-of-plane bending moment. So what we are talking about is something like this. So if this is the shear, the bending moment should be in this plane here, right? And this bending moment here in this direction or in the other is going to induce some stresses in which layer? The stress will be in this direction, so the resisting layer will be these two here, like before, exactly like before. So those are the effective resisting layer. Okay? Okay, now we need to calculate the distribution of tau, tensile stresses, in a cross-section made by two rectangles at a certain distance to each other, which are in some way rigidly connected because we assume that there is a validity of the plane section will remain plane after the deformation. Okay, so this is the resisting cross-section. Now I'm asking to you, based on what you remember for mechanics of materials, how can I calculate the distribution of tau? So tau equal, we use the Jourowski equation. You remember by heart the Jourowski equation? I think you should after mechanics of structures, probably. So the shear stress is equal to tensile force, shear force times the first moment of area of, let's call this one x, of the part of the cross-section divided by the fiber. So remember, we need to take, if you have something like this, you need to find the neutral axis, x, and then you need to say, okay, I'm going to calculate the tau on a certain fiber, distance, let's say, y from the cross-section, so this will be x, s, I want to find the tau on this fiber here, so I need to calculate the first moment of area of the part of the cross-section either above or below the fiber, for example, this part of the cross-section, with respect to the neutral axis. So this will be first moment of area of the part of the cross-section above the fiber, for example, with respect to the x-axis, which will be a function of y, of course, divided by what? So? The second moment of area of what? Of the resisting, or we call it effective cross-section, with respect to neutral axis. And in this case, the neutral axis would be the centroid of the resisting cross section, which is also the centroid of the cross area anyway. So Jx time. Then I would call it not the thickness, perhaps I would call it the breadth of the width of the fiber. So B. Usually, since these are two-dimensional structure, usually we do this verification per meter. So we take B equal to 1 meter, just to simplify. Okay. Good. Now, the diagram of the tau. So which value do we have here? We start from the top fiber. Which value of tau can we expect over here? Zero. Why 0? Because this fiber is here. So the first moment of area of what I have above the fiber, 0, with respect to the neutral axis is 0. So if this is equal to 0, we start from 0. Okay? Same thing will be here, obviously. Okay? Good. Now, how is going to change as I reduce the fiber? For example, if I have a fiber here, which kind of variation can I expect? So how does this function vary with y? Parabolically. So second degree function. So I will have something like this. Okay? Then when I go below this resisting cross section, how is going to change the first moment of area? How is the first moment of area going to change if I consider some fibers here? So, constant. So, it's like, if you remember well, when we studied the second stage of the reinforced concrete structure, so we were talking about calculating with Jurafsky the stress, the shear distribution of stresses for a crack cross section. For a crack cross section, in the crack region, concrete was basically was there but was not resisting, so the trend, the diagram of the tau was constant. And so it is here. So this is the diagram of the tau. Okay? Tau for a 3-layer cross compartment, which is very much used for walls. When it comes to floors, the 5-layer is the most used one, because for floors we need more stiffness in some way. So for 5 layers, how is it the trend of the tau? For 5 layers, we have a slightly different trend, so we have to keep in mind that here, this time we have 3 resisting layers. So parabolic distribution, first layer, then constant because it is the non-resisting layer. Then the third one, we have another parabolic distribution, but as you can see here, the temperature is much lower. Why is much lower? Because here we are much closer to the neutral axis, so the variation is very little. Then again constant, and then again parabolic. Now, if we had, suppose we had the out-of-plane shear acting in the other plane on this 3-layer cross section. So we have a situation like this. Okay, so in this case, shear force, bending moment, means that this is the only resisting layer. So how will it be in this case, the diagram of the tau? after the consultation, what can you tell me?
Parabolico sono sullo stato.
Parabolic only, this is a rectangle, so we know very well the solution. It's a parabolic, no? So it's very simple. So here, 0, 0, and parabolic. Okay? Okay, now, if I have to ask you, where would you check the shear strength? So where would you do the ultimate distance verification of shear? Which fiber? In these three different pages here. If you look at the strength demand, so where do we have the maximum demand of shear stresses? Here, here, and here. So, which fiber? Okay, so let's go to C. Starting from here. Here, well, we have several fibers. So the whole layer, if you want, the whole inner layer is loaded with the maximum shear. But for sure, we are going to have a check here. Now here, in the middle only, and what about here? In the center fiber, okay? Now in this case here, just note that the difference between the central layer and the two inner layer is not much big. So you can see here, of course, in the central layer, a slightly larger shear demand than everywhere else. Okay? But of course, I agree with you, this is the maximum shear demand. However, what is going to be different now, what we are going to see now, is that the shear strength demand will be, the shear strength capacity will be completely different in this layer and the other two layers. Why is that? Because of the orientation of the fiber. So, if you remember, at the very beginning, when we were talking about shear, we said that the shear resistance is very different if you have a shear that tends to cut the fiber. So, for example, if you remember, we did this micro model with the fiber of wood oriented in this way, surrounded by a less resisting matrix. So this is in some way the micro model of wood. And we said that these fibers here are very strong, but this matrix, called middle lamella, is very weak. So we said that if I have a shear, for example, around this plane, so if the shear plane tends to cut the fiber, then the strength is very big. Because the shear resistance depends on the strength of the fiber. However, the shear resistance is lower, much lower, if the shear plane cuts only the middle lamella, like in this vertical plane. And we also said that in this case, it's not the same having a plane which is oriented along the radial direction of the load or along the tangential direction of the load. So in other words, if this is the trunk, so this is the load, so the shear plane, if the shear plane is parallel to the tangential plane, like here, the shear, and this is going to cut directly only the middle lamella, the shear strength is much lower than if we have a shear plane oriented along the radius. So in the other plane. In other words, what I'm trying to say is that if we look at the arrangement of the grain in a cross-lamp panel, consider that this is a longitudinal cross-section of a cross-lamp panel subjected to bending and shear, so this is the shear. First of all, we need to keep in mind that if we have shear stresses in the cross-section, we have also shear stresses in this direction, because if you remember, there is this property called reciprocity of the tangential stresses that comes from the fact that the Cauchy tensor is symmetric with respect to the diagonal, meaning that tau zx equal to tau xz, or tau zy is equal to tau yz. So meaning that if this is my beam, subjected to bending moment, for example, and shear force, and here I have 3 layers. So this layer is parallel to the grain. Here we have a layer perpendicular to the grain. Here we have another layer parallel to the grain. On the cross section we have some tau distribution. Okay. So this tau, for the reciprocity of the shear, we have also some tau distribution inside here, acting in this direction there. So in other words, if I isolate the part of this beam which is above this plane, I have a situation like this. So here I have a tau, and I have also a tau here. Okay? So these tau are exactly the same. So this tau that I have in this direction, they cannot provide any failure for our beam, because as you can see here, those tau tends to break the fiber. So this micro model of wood here would be something like this. So this tau here tends to break the fiber, okay? So we can't have failure in this direction. If you remember, we discussed this several weeks ago. However, this other tau here, they are, in this case, the fiber are oriented this way, here in between. So this is the cross section. Here are the fiber, and the shear tends to break the middle lamella. Okay? And in this case, as you can see here, the plane of shear is a plane oriented in the tangential direction, because you see here the growth 3, so we have the tangential direction for the intermediate layer. One is that for the outer layer, here the fiber are oriented this way. So in this case, we have already shear, we have again a shear plane that tends to break the middle lamella. However, this is not in the tangential direction, this is in the radial direction. So, by doing some experimental tests, it was demonstrated that if the shear is applied in the tangential plane, then it's what we call rolling shear, and the shear strength is much lower compared to the shear which cut again the middle lamella but is oriented in the radial direction. Okay? So, looking at how the layers are arranged, it appears clear that all the layers that are perpendicular to the grain will be subjected to rolling shear, while instead the layers that are loaded parallel to the frame will be subjected to longitudinal shear. Now, if you look at the value of strength for rolling shear and longitudinal shear, you will find that for rolling shear, more or less 1 Newton per square millimeter, so very low value, and for longitudinal shear, let's try to see. For longitudinal shear, we are talking about 3.5 Newton per square millimeter. So, the longitudinal shear is, I would say, roughly speaking, 3 times more resistant than rolling shear. So, if you go back to our case, you see here. So, for example, first case. Here we said that in this first case, the maximum shear demand is in the inner layer. In the inner layer, I will have to compare the shear strength, so the shear demand, with which strength? With the rolling shear or with the longitudinal shear? C is the wood. It's basically arranged perpendicular to the grain. In this case, I will have to take the rolling shear or the longitudinal shear. The rolling shear. Okay? So here I will have to check for shear, for sure, the inner layer. So shear strength demand in the inner layer, which is also the maximum shear stress, less than or equal to the rolling shear resistance. Second case, only one layer exists in the middle one. So in this case, which kind of verification will I have to do? So here I have a shear, the maximum shear strength demand, the maximum shear demand is in the inner layer. The inner layer is stressed due to shear. The inner layer is stressed to we will have to check this maximum shear strength demand for rolling shear or for longitudinal shear. In this case. Rolling. So now, one said rolling, the other one said longitudinal. So let's try to find an agreement. Okay, these two are not loaded. Now this one is loaded. So if it's loaded with shear, now I need to check what's happening in this direction here. So in this direction, the configuration is this. And I want to do the verification you told me here, where I have the maximum shear effect. So in this case, do I have rolling shear or longitudinal shear? Rolling. So now you change your mind. Now, this is a transversal cross-section. This is a transversal cross-section when I consider that this is the only resisting one, but the longitudinal one is this. So it's rolling shear. So also here, rolling shear. Okay? Now we go back to this case here. Here we have the maximum shear demand in the inner layer, which will be loaded in longitudinal shear or in rolling shear in this case. So this again, this is the cross section like here. So I need to see what's up in the other direction. Okay, now, this is the third case. So in the third case, I have basically longitudinal. So this one is a cross section like this. So this is the cross section. If I take now longitudinal cross section, the longitudinal cross section will be this way, will be the other way around. So this is the longitudinal cross section. I will have basically something like this. Okay. And I think that also this we made a mistake. I will go back to this later on anyway. So this one. So the maximum shear stress demand is here. So this is the transversal cross section, this is the longitudinal one. So in the longitudinal one, if I do a shear plane here, what are we going to have? Rolling shear or longitudinal shear? Longitudinal, okay? So this is longitudinal shear. So the maximum shear stress that I have here will have to be compared with the shear strength for longitudinal shear. While instead, this other value, which is slightly lower, will have to be compared. So if I do a plane here, this value will have to be compared with what? Rolling shear. Now, since the factor between rolling shear resistance and, let's say, longitudinal shear resistance and rolling shear is 3, it's clear that the most governing verification will always be rolling shear in this plane, where I don't have the maximum shear demand. Okay? Now we go back to here, this one, because here we made a confusion. So here, this is the longitudinal cross section. Sorry, this is the cross section of the section. So the longitudinal cross section here is something like this. So I do the longitudinal cross section here. I have something like this. So now if I do a shear plane here, what do I have there? Longitudinal shear or rolling shear? Longitudinal. So you are right from the very beginning. Okay?
Can be a case when the shear in the part where we have rolling shear,
Yes.
is less than 3 times than the shear on the...
Never, because you see, it's very small.
So
The only, I'm just thinking about if you have 7, it would be anyway, because if you have 7, no, I can't see of any I mean, formally you have to do both, but I'm fairly sure that's always what is governing this one, unless this case here, where you don't have rolling shear, only longitudinal shear. Okay? So, any question with longitudinal shear, rolling shear? It's a bit, as you can see, it's very simple to get confused with this. You need to remember that one thing is the cross section, one thing is the longitudinal cross section. The two are opposite in some way. But to understand if there is rolling shear or longitudinal shear, we need to take into consideration the longitudinal cross section, not the transversal cross section, where we usually draw the stress distribution. So in general, you see here the value for the rolling shear is twice as much as the tensile strength perpendicular to the brain, so very low value, 1. While instead the longitudinal shear is more or less 3.5, the same values for blue. And also here, if you look in this table, you have also the value of rolling shear and longitudinal shear among the different parameters that are needed. Okay? In order after to calculate, for example, if you need to calculate the deflection of a cross-lamp panel, you can make again reference to this simplified model. So just consider the resisting cross-section or effective cross-section, just to write down the effective flexural bending stiffness of the resisting cross-section, which would be E90, sorry, ED0, so the mean value of Young modulus parallel to the brain times the second moment of area of resisting effective cross-section. Okay, so if you don't have any other further question, I think we can now start talking about seismic design. So in terms of seismic design, the only thing you know so far about seismic design is what we said last year, so in the course of reinforced concrete design in the third year, right? Because you haven't done dynamics of structure so far. I think you're going to do it next semester, right? And you haven't done earthquake engineering either, so we need to perhaps refresh a little bit our knowledge about seismic design. So, I would say, first of all, seismic design can be made according to two very different approaches. One approach is a kind of elastic design. So if I have a brittle structure, so a structure that cannot dissipate energy, then I need to use the pseudo-elastic design spectrum. The same that you're going to use for your project. So for your project, you assume that your structure is brittle, even if it is not. So you assume your structure as a brittle, so doesn't have any capacity to dissipate energy, meaning that you have to take the full elastic forces into consideration. They're actually not the real full elastic forces, because according to the regulation, they say that even with a brittle structure, I can make reference to a so-called pseudo-elastic design spectrum, where I divide the elastic value of the spectrum by 1.5. This 1.5 takes into consideration that we have always some additional margin of safety and strength due to the fact that I have all these safety factors and so on. Of course, in this case, I am going to design for the full earthquake action, and I will end up with larger cross sections, okay? Because I'm not taking into consideration any possibility of the structure to dissipate energy. So my design will end up with larger cross sections. The other possibility, which is actually the most common, is also the one that you followed when you design your reinforced concrete frame 2 or 1 year ago. In that case, what you did last time, if you remember, you said, okay, I'm designing a reinforced concrete frame, for example, a moment-resisting frame, which can dissipate energy if I design it properly. So if I design it properly, this moment-resisting frame can dissipate energy under an earthquake. And so, I can, by dissipating energy, I can reduce my design seismic action. I can reduce by which factor? More or less by what we call the Q factor, so the behavior factor, which ranges between 2 and 5. So what was the value that you used for your frame, for example? Just to see. 5.85. 5.85. So it's very high value. For high activity. So 5.85, which is more or less 6, is an extremely high value. It means that you need to be, because it means that you consider only 1/6 of the whole, let's say, elastic seismic forces, and then you need to provide some ductility, very important ductility values in some regions. Which region? Well, in your case, when you find your ductility to make sure that your structure can dissipate energy in order to reduce by a factor of 6. So you had a moment-resisting frame, and the ductility, sorry, let's reduce. Sì. Sì, sì. Ah. Alle 11, sì, sì. Perfetto. Io sono nella B012. Se vuoi puoi venire anche qua direttamente perché non ho problema. Sì, sì, pure sono qui. Benissimo, grazie, ciao, ciao. Sorry, non c'è stato. Okay, what I want to say, we said before, we have to reduce by a factor of 6, almost 6, the spectrum, the design spectrum, and so we need to have some energy dissipation in some region. So in which region we could find some possibility to dissipate energy. Eh? Exactly, because before you said nodes, which is incorrect. If you want to be rigorous, it's not the node itself, it's actually the beam, the cross section. Actually, it's not a cross section, it's the length of the beam, which is more or less 1.5 or 2, the effective height of the beam, at the section with the beam and the column. So it's actually located, the plastic is located on the beam, but very close to the column, to the node region. So we have, with capacity-based design, we need to make sure that this zone can dissipate energy. For example, using very dense steel roots and checking the ductility and so on. Okay? By doing this way, of course, we can design for a lower value of the size of the forces. And we also accept, we accept that if an earthquake is a strong earthquake, the desired earthquake occurs, at the end of the earthquake, of course, we will have a structure which will be highly damaged, because this cross-section here will be highly damaged. The bar will be probably yielded, and probably the building will be not straight anymore, but will have some out of plan, if you want, okay, at the end of the earthquake. Of course, we can earn some money because we can use, in this case, since they're actually smaller, we can have some smaller cross-section. However, possible damage after the earthquake. Okay, so those are the two different design philosophies. I would say that the most used one is the second one. So we will have to see now how to adapt this design philosophy that you already know for reinforced concrete to the case of timber. Because for timber, in timber at least, we don't have rebars like for concrete. If you remember, for reinforced concrete, all your ductility was coming from the concrete or from the steel? From the steel. So concrete was actually a brittle material, the steel was darker material, and we would have to take into consideration some possibility. For example, we had to prevent shear failure, because shear failure is always brittle failure, using capacity-based design. So we have to see now how to adapt all this design philosophy to the case of timber. Take into consideration that in timber we don't have steel rebars. However, in timber we have some steel members, right? Which member we have? Which steel member do we have in the timber structure? The joints, more than the joints, I would say the fasteners. So in the joint region we have some fasteners, which are usually made of steel. So the idea would be, if I can make sure that I have, rather than plasticization of rebars, plasticization of fastener, this plasticization of fastener may in some way replace the plasticization of steel that I don't have, and of the rebar that I don't have, and I can get some dissipation, energy dissipation, so I can also there have a plastic design, and so to use a Q factor. Now, some basics, if you want, about seismic resistant timber buildings. First bullet point, very important, we need always to keep in mind. With respect to reinforced concrete, we know that timber structures are very lightweight. So we said from the very beginning that a timber structure weighs more or less 1/5 of a reinforced concrete one. And since we learned that the seismic forces are roughly proportional to the weight, on a timber structure I can expect that I will have a seismic force which will be much lower than on a reinforced concrete structure. And this, of course, is an advantage. However, we also learned that the failure of timber structure in general is brittle. So we don't have, when we test the timber beam, remember the timber beam that we saw last week? And when we applied the load this week, I remember the both of it was last week. When we applied the load, in the end, of course, we have a significant, still an important deflection, but in the end, there was quite a failure, an abrupt failure at the end. So, in general, timber members have brittle failure, and so they dissipate little energy. So if we started to do cyclic tests on this beam, we would have found very little energy dissipation, and this is a disadvantage. In fact, energy dissipation is a prerequisite for having an effective seismic behavior and for using a behavior factor. So for reducing basically the value of the seismic forces applied on our structure. Now, how can we obtain energy dissipation? We have also here two different philosophies. One possibility is to introduce in a structure which is elastically designed one or more energy dissipators. So, we can say, okay, I design my timber structure and all the different timber members are designed elastically. However, I added some devices in different locations that are able to dissipate energy. So in this case, I get the energy dissipation that I need to reduce the elastic forces by the behavior factor by locating in certain points of the structure some energy dissipators. What can be energy dissipated? For example, as I showed you, if you remember yesterday, the day before yesterday, in this building here, which is constructed in New Zealand out of laminated linear lumber, there are walls made of timber which are pre-stressed. And between the walls there are those metal devices. Those metal devices, when the walls rocks, so when they move with respect to each other, those devices are going to deform. And they plasticize. By plasticization still, you can get energy dissipation. So by placing more of those devices, you can make sure that during an earthquake, the structure as a whole will dissipate energy. The timber will still remain elastic. So in this case, we have all the timber members during an earthquake remain elastic. However, we have energy dissipation coming from the plasticization of those steel devices, U-shaped metal dissipator. Okay? This is one philosophy of design. Alternatively, I would say more commonly, beyond timber structure, we can exploit the energy dissipation, as we said before, of metal fasteners used in the connection region. So, in a timber structure, anyway, since the timber structure is a prefabricated structure, so anyway it comes from joining more pieces of timber. So the idea is that in the joint region, I will have some metal fasteners, nails, screws, dowels, bolts, whatever you want, and I can exploit the possibility that those fasteners may plasticize during earthquake. So may provide the energy dissipation that I need for getting a dissipative behavior. Of course, this means that when I want to design my connection, I will have to be careful, because I will have to make sure that the failure type of my joint is characterized by plasticization of metal fastener. If you remember, when we derived the Young's equation, not all the failure modes are characterized by fastener plasticization. For example, when you have a joint like this, timber member, and a fastener here. You remember there are 6 different failure modes here, but only 3 are characterized by fastener plasticization. For example, I can have a bedding on one timber member, where I have no fastener plasticization, and bedding on the other one, and I have, okay, let's do the other way, sorry. Embedding here, I don't have any fastener plasticization. I can have a bedding with global rotation of the fastener, also here no fastener plasticization, and then I have the other 3 modes where I may have one plastic each here, one plastic each here, or 2 plastic each. So if I want to have a dissipative structure, when it comes to designing this kind of connection, it will be not enough to check that, let's say, the design shear force in the plasticization is less than the, okay, put in this way. The shear strength capacity of the connection itself. I will also need to make sure that I have 1 or 2 plastic hinge formation in the fastener. So this is a further condition I need to check. If I want to consider this connection as a dissipative, and if I want to be able to use the behavior factor Q larger than 1.5. Okay? And of course, I will have to prevent in this connection rituals or any kind of brittle failure mechanism like splitting the wood and so on. I will also have to do, like you did for your frame, reinforced concrete design, we'll also have to think about how kind of global plastic behavior I can achieve on the structure. So it's not only a matter of saying, okay, I have a number of joints and I design all of them as a ductile. I need to control that the global behavior of the structure will behave as a ductile. So we have to ensure that I have a global plastic behavior of the structure. And then, like you've done for your frame, I will have to make sure that all the possible brittle failure mechanisms are avoided. Now, going back to your design, the one you did for reinforced concrete, can you remind me how you did your design? So, you started from a frame, then you chose one ductility class, for example, high or medium. Then you calculate the behavior factor, you calculate the elastic forces, and then for those elastic forces, you design what kind of member. For example, for the beam, did you design the beam for the stresses coming from the reduced elastic forces, and for which kind of verification you did for those forces? So in other words, once you did the analysis, for example, with sub 2000 of your frame under your reduced seismic forces, you calculate the shear, the envelope of the shear, you calculate the envelope of the bending moment, and then you did the design, for example, of the beam. So, first of all, you design the beam for what? For bending moment or for shear? For bending moment. And when you design the beam for bending moment, particularly when we design these critical zones, you took into consideration the value of the bending moment coming from the analysis. So the one coming from the reduced elastic forces. And in this way you did the design for bending. Okay? Then, when it came to shear, what did you do that time? Did you take the envelope of the shear forces, like you've done for the bending? Yes? Okay, perfect. So you didn't take the results of the analysis. Why you didn't take the results of the analysis?
Because we had to guarantee that the failure for shear after the...
And why you wanted to guarantee that you had to guarantee that the failure for shear will occur after one for bending? Why is that?
Because shear is a brittle mechanism.
Because shear is a brittle failure mechanism. Exactly. So what you need the design of the ductile members for basically the reduced seismic forces. But then you couldn't design also the brittle members, in this case, for example, the joint or the column or the shear for the same forces. Because if you had done it this way, then you would have had the same probability to have a brittle failure or a ductile failure, which is not good. Because instead you have done all your design assuming that you have a ductile failure. Otherwise, if you had a brittle failure, you would have to design for bending, not for the reduced seismic forces, but for the actual elastic seismic forces without the behavior factor. Okay? So here we will have to do the same. So we will have to identify a brittle failure mechanism. For example, in your case, the brittle failure mechanism was a frame with a plastic hinge at the base of the column and at the intersection between the beam and the column themselves. So this is the ductile failure mechanism. Then you design the member for the reduced elastic forces, and then you have to oversize, so to over-design all the brittle members in order to make sure that this kind of brittle failure will never occur before the other one. Okay? Here we have to do the same. So here we have to identify a general ductile failure mechanism. Once we have found the ductile failure mechanism, we can design the ductile members. In our case here will be the joints. So while for you, the ductile failure, the ductile region were on the beam, in our case, and then you have to oversize the column and the joint. In our case, the ductile member will be the actual joint. So the beam column joint will be our ductile member. So we are going to design this for the reduced cyclic force. And we will have to make sure that in the ductile failure member, we have one or two plastic disc formation in the fastener. Otherwise, it doesn't work. And then, we will have to design all the possible brittle member for an overstrength. Like we've done before for the shear. You didn't design for the shear. You design for the shear coming from the equilibrium, where we are going to consider the resistive bending moment of the pier amplified by the overstrength factor. So here we will have to do the same. We will have to define the overstrength factor of the joint and to apply this overstrength factor of the joint to all the brittle members. In our case, for timber, the ductile member will be the joint, and the brittle member will be the beam and the column. Okay? So there is a significant difference with respect to steel and reinforced concrete. Because in steel and reinforced concrete, the ductile member was the actual beam. In our case, the ductile element, the sympathetic element, will be the joint. While instead, the beam and the column themselves will be regarded as a brittle member. It will have to be designed for the overstrength of the connection. And also this failure mechanism not ductile, so this failure mechanism which are not ductile, will have to be designed for the overstrength of the ductile failure mechanism. Because we want to make sure, if you use a Q factor of 3 or 5 or 4, that we never have a brittle failure mechanism in our fastener. Okay, it's clear? There will be, in our case, the overstrength factor. We have to take into consideration that there is a very important scatter of material properties between the 5th and the 95th percentile. So in other words, in our case, this one we're going to see later. When it comes to calculating the overstrength factor, we will have to move from the lower 5th percentile to the upper 5th percentile of strength. And since timber has a big scatter of material property, this value of the overstrength factor will become important. You remember how much was the overstrength factor for reinforced concrete? So, 1.25, yes. So you took your resistive bending moment, multiplied by 1.25. Me, I don't remember that. That's why I asked you. But I think that the value is more or less, yeah, 1.25. I think it's reasonable. Okay, for timber, we will find a value which will be in some cases 1.6. So we will have to oversize quite a lot. Why so high value? Because we will see that the overstrength factor is the ratio between the lower 95th percentile and the lower 5th percentile, and for timber, since we have an important scatter of material property, we get to 1.6. So we need to, some way, we need to be aware that when it comes to capacity-based design for timber structure, this means that we need to oversize quite a lot, much more than what we used to do for reinforced concrete. Okay? So this is an example of capacity-based design, what you already know. You know about capacity-based design for reinforced concrete. Now you need to transfer this concept from reinforced concrete to timber. Where basically what changes is the failure, kind of failure mechanism if you want. So, suppose you want to design a moment resisting timber frame, like this. So this is a kind of connection, high ductility connection. So, we know that if we do some cyclic test on this joint here, we get this kind of behavior, very ductile as you can see. We can approximate this behavior, the cyclic behavior, with an elastoplastic force displacement relationship. In this case, actually, it's not force displacement, it's moment rotational relationship. So we have the ultimate bending moment and the ultimate rotation, relative rotation of the joint. And then we need to consider different possible plastic mechanisms of this frame. So this is our frame that we want to design. The effect of a seismic of an earthquake are in some way is schematized with in an inverted triangular distribution of horizontal forces, and here. And then we need to consider what kind of plastic mechanism to design this frame for. First type of plastic mechanism could be the global mechanism, the same that you use for designing your reinforced concrete frame. This is exactly the same. You see you have a plastic hinge at the base of the column. And then, if you remember, for reinforced concrete, you have a plastic hinge formation on the beam close to the column. In our case, we won't be able to have this plastic hinge formation on the beam, but we will have the plasticization of the whole connection. Okay? So in our case, the whole joint will plasticize, not the beam of the column. So the whole joints will plasticize. Of course, if we have a global plastic mechanism like this, if we do what we call a pushover analysis, so if we basically increase all these horizontal forces by keeping the ratio constant over time, we will end up with a diagram like this. Elastic initially, and then when the joints start plasticizing, since the joint has an elastoplastic behavior, then we have a simultaneous plasticization of the joints, and we end up, you see, with a global elastoplastic behavior. So in the end, we will have, as you can see, one deflection on top of the building equal to VA. Okay? This is not the only plastic mechanism we can have. In fact, we could have also not another plastic mechanism, which is a partial, or what is called a storing mechanism. So we may have a plasticization only, for example, of the column here, on two stories. In this case, even, or let's say also the plasticization only of two of the joints, even if the angle theta u was the same, of course, in this case, since we have a plasticization only of one story, in the end we would end up with a global displacement on top of the building equal to VB, with VB significantly lower than VA. Now, among those two different plastic mechanisms, we need to select the one that can ensure the maximum energy dissipation. If you think about having some cycles, it's clear that the second plastic mechanism, the storage plastic mechanism, will provide a much lower energy dissipation compared to the first one. So among the two, or between the two different plastic mechanisms, we should select the first one, because the first one is the one that will bring us more activity and more energy dissipation. What does it mean? It means that I will design my structure for this plastic mechanism. In particular, I'm going to design the joints for the value of the seismic forces calculated using a high value factor. But then, when it comes to designing the beam itself and the column, I will have to design the beam and the column not for this value of forces, but using capacity-based design. So by the overstrength of the single joints, so of the value of the member that I want to plasticize. Okay, so in this case, I'm going to consider that the columns and the beams will have to be designed for the overstrength of the joint. And as I said before, I'm expecting to the value of the overstrength factor much higher than for reinforced concrete. So just keep in mind what is summarized in this slide here. That's the capacity-based design principles are always the same. However, in this case, the plastic mechanism is different. So while for reinforced concrete and steel, the plastic hinges are always located in the beams close to the joints, and the column and the joints are oversized, are overdesigned for the overstrength of the hinge. For timber structure, the dissipative members are always the joints, and the beams and the columns are always designed for the overstrength of the joints themselves. Okay? It's quite significant difference. Now, summarizing the methods of seismic analysis.
Sorry.
Yes.
But you can achieve the global mechanism of timber.
Yes.
But if the node plasticized, how can you achieve it?
Because basically the plasticization of the joints is related to a relative rotation between the beam and the column. In the end, the plastic mechanism in timber can be considered this way. So I cancel this. So this is kind of structure of plastic behavior. If you want, you can assume that the beams and the columns, they don't plasticize, so they remain elastic. They are pin connected. However, here there are some rotational springs. Okay? The relationship between these rotational springs, if you want that for each connection, you have a M theta relationship, which is something like this. So this is the model of your structure when you design the timber structure as a dissipative, with a dissipative behavior. So columns and beams will end up behaving elastically, and they will have to be oversized. While instead the only dissipative behavior would be this rotational springs here, schematizing the joint. It's clear now? Well, instead, if you remember, for reinforced concrete, you have a slightly different behavior. Okay, so methods of seismic analysis. So far, I think you have learned only one method of seismic analysis, the one that you used in reinforced concrete design, which is the linear static or lateral force method of analysis. So the idea is, first we calculate the seismic weights on our structure, where the seismic weight is the permanent load plus one part of the variable load. So it's very similar to what we call quasi-permanent load condition. Then we derive the elastic spectrum, which depends, of course, on the seismicity of the area, on the subsoil, and so on. And then we move from the elastic spectrum to the design spectrum by making some assumption on the dissipative properties of our structure, and so on the assumption of a certain value of the behavior factor, which is stable. Then we calculate, we estimate the first vibration period of our building, for example, using this for this rate of semi-empirical formula here. We enter into this diagram and we find out the ST, so the ordinate of the design spectrum, which will give us, which will provide us with a value of the acceleration in some way of our structure. Then we calculate the total base shear by multiplying, you see, the total mass which is the seismic wave divided by the seismic acceleration times the acceleration as b per t1. And then we distribute this total shear according to this inverted triangular distribution of the different story. Okay? Do you remember this? This is what you were supposed to have done in reinforced concrete design. You four guys, you already spoken about seismic design in some courses. Your degree, you didn't talk about seismic design? No. Okay, so you have just the basics here, of course, and then there will be another course dealing with this. In the second semester, there is a course called Dynamical Structures, where there will be some basics also about seismic design. And next year, there is another course called Earthquake Engineering, where we deal explicitly about this. Okay, so this is just some basics that are needed to understand what we are talking about. So the linear static analysis, which is the simplest one and the most common one, so of course, at the end, once I get this distribution of forces, I need to solve my structure to find out the bending moment, demand, axial force demand, and the shear force demand, and then I do the ultimate resistance check in the different section. And of course, if I have to do capacity-based design, then I have to design some of the methods using capacity-based design. So, for the linear static analysis is the most common used method, but cannot be used always. This can be used if I have a structure with a building which is regular in elevation, which doesn't have too many different, for example, overhangs or something like this. And of course, if the building is also regular in plan, I can use, rather than a space model, I can use two plane models that look independent in two different directions. Then I have what is called linear dynamic modal response spectrum analysis. We just mention here this, we don't go into details, because this will be dealt with extensively in the course of dynamical structure that we're going to have next semester. So linear dynamic or modal response spectrum analysis is another method where basically we always start from the design spectrum. However, in this case, rather than do a static analysis with sub 2000, we can also do this analysis with sub 2000, but the idea is that we estimate by modal combination of max displacement, max internal force, and max stress. I don't say anything anymore because you are going to study this next semester, so there's no point to spend more time here. And this is actually mandatory if you have non-regular buildings. So if you have non-regular building, we need to use the linear dynamic analysis, which is more complex and which can be done basically using only software. Then we have nonlinear static pushover analysis. Also here I don't want to say anything. Actually, I'm not saying anything because it's again something we're going to learn later on. We don't need for this course. And we can have also nonlinear dynamic analysis. Nonlinear dynamic analysis means that with the software we simulate an actual earthquake occurring on our structure. So we have our model, we apply the earthquake on the base of the model, we study over time, so we need to have an acceleration, and we study over time how are the time history of displacement, internal forces and stresses. Of course, to this course, the most interesting method are the first two, but particularly for this course here, we are going to use only the linear static analysis. The linear static analysis, the one we are going to use for the design project, and perhaps for the second project, the one that we will do about a small cross-lamp or lightweight frame construction. Something we will do actually by hand. Okay, so this second project, I would like that you do by hand. So it will be something much simpler compared to the other one. So you won't have 100 law combinations, you have just one law combination, just to understand how by hand to calculate the different forces at the different levels of the building. Now, something about the regulation, Italian regulation and European regulation. So, the European regulation talk about significant damage and damage limitation verifications. So, when we do a seismic design, what do we have to do? Basically, we have to do a linear static analysis using the design spectrum, and we have to check two limit states. One is an ultimate limit state, which is called significant damage, in Italian salvaguardia della vita, and based on your design spectrum, you basically go to the different members of your structure, for example, node down, you calculate the force demand in the node down, you compare it with the strength of the node down itself. So you do just a strength verification. And then we have to do another verification, which is a serviceability limit state verification, which is called damage limitation, o stato limite di danno in Italia. In this case, we consider a lower intensity earthquake, so not an earthquake with a return period of 475 years, but an earthquake with a return period of 50 years. We were going to check that under this reduced intensity earthquake, the interstory drift, which means basically the relative displacement of one floor with respect to the other. So, for example, if you have a frame like this, during an earthquake, I can expect that this floor will have deflection like this. And what I'm interested in is this relative displacement of one floor with respect to the other. So I'm not so much interested in the total deflection on top of the building, for example this one. I'm not so much interested in this value. I'm interested more in the relative displacement of one floor with respect to the other one. So this one, for example, or this, those are called interstory drift. So, what we said before, we will have to consider a reduced intensity earthquake motion. So, the spectrum in this case will be lower, the design spectrum will be lower. We consider an elastic behavior of our structure, and we go to calculate this interstory drift. So, this relative displacement of one floor with respect to the other. So, these interstory drifts are called, for example, dr. And we will have to check that dr shall be less than or equal to dr max. So there will be less than a maximum, a certain limit provided by the regulation. Why do we want to do this verification? Because we want to make sure that if we have a reduced earthquake, for example, if like we had this earthquake in Amatrice, which of course was a destructive earthquake in Amatrice, but not a destructive earthquake in L'Aquila, which could be considered as a, let's say, serviceability limit state earthquake, we don't want to have too much damage for a reduced intensity earthquake, because it means that if we have too much damage every time, we need to spend money. Okay? The damage can be limited by controlling the interstory drift. For example, if you have a partition, internal no structural partition, the damage is limited by the interstory drift, because this partition, the possible damage on the partition depends on the interstory drift. If the interstory drift is too big, this partition tends to be subjected to some relative displacement, and then we can have some formation of cracks or other things. So, for example, let's go here. You see here, this is taken from the Italian regulation for claddings. For brittle frac, you see here, if you use brittle claddings, like we do often in Italy, then this dr shall not exceed 0.005 times the edge. If you have a 3, let's say you have if you have a 3 meter high interstory, 3 meter interstory height, so 0.05 times 3 meter becomes let's see, so if it was 1, this would be 3 meters divided by 1000 would be 3 millimeters, right? So 3 millimeters means 15 millimeters, if I've done right the calculation. So, is right? So let's say if this was 0.001, it means it's 1 over 1000. So 3 meters divided by 1000 is 3 millimeters. Since this is 5, so 3 millimeters times 5, 15 millimeters. It means that if I have a brittle cladding, I can accept no more than 50 millimeter years of interstory drift. So during an earthquake, this floor here shall not move more than 15 millimeter relatively to our floor. Okay? Because otherwise, actually this is also 4 meters, it will be more than probably 20 millimeters, if there's not 3 meters, 4 meters. But anyway, this is a kind of limit that we have to check. Because this is limit, it's not because we are concerned that the structure may fall down, but because we are concerned that this partition may crack. And then if they crack too much, after we need to change them, or we need to retrofit them. So in general, when we do a seismic design, we need to check both ultimate limit state and serviceability limit state. They are called damage limitations, they are called limit state, they are called significant damage, ultimate limit state, and the other one is called damage limitation, verification. So both of them must be verified. Of course, if we design a timber building, there is no point to design a timber building to place inside the timber building a brittle cladding system. For example, using tiles or bricks. With the timber buildings, usually we use gypsum plasterboard, for example. So materials, so materials that can easily accommodate this kind of relative displacement. So for timber, the limit can be increased. You see, we can move from 0.005 to 0.01, which means that for timber, we can accept up to, on a 3 meter interstory height, we can accept up to 3 centimeters of relative displacement, so of interstory drift. Okay? So we are a little bit more tolerant for timber building. Okay. About the behavior factor, what is the behavior factor? The behavior factor is, as you learn in reinforcement design, is a reduction coefficient applied to the elastic spectrum and therefore to the seismic action, such that a structure elastically designed under this reduced seismic action can withstand the design earthquake, although significant damage without failure. So in other words, it's, if you want, a simplification that we do of a problem which would be complex, should be treated as a nonlinear problem, where we said, okay, I do an elastic analysis, because I want to do a nonlinear analysis, too complex, I do always an elastic analysis, I do an elastic analysis under a reduced seismic forces, which accounts for the fact that my structure can dissipate energy. So in the end, my structure will survive the earthquake, even though it will be very much damaged. Of course, a crucial point when you do a seismic design is the choice of the behavior factor. Now, which value of behavior factor we should be choosing when we design timber structure? The Q factor in this case are taken the Eurocode 8, and it depends on the structural system. For example, 2 for crossland buildings, 5 for right frame buildings. So there is this table. If you look into the Eurocode 8, which is the European regulation for seismic design, you find this table here. Where, for example, you see that for cantilevers, beam, arches, 2 or 3 pin joint, Q is equal to 1.5. For glued wall panels with glued diaphragm connected with nails and bolts, which is extra, is 2. And for nailed wall panels with nailed diaphragm connected with nails and bolts, diaphragm system is basically 5. Okay, so the values that we can choose are tabled into the Eurocode 5. Note that those are upper limit values of the behavior factor. So they are upper limit, means that we cannot exceed those values, but we can also use lower values. If you look at the table from the Italian regulation, from the 2018 Italian regulation, you see here we have two ductility classes, ductility class A, which is the highest one, and ductility class B, which is the lowest one. So for light frame structure, we have 5 and 3. And for X-lam, we have a new line where we have for X-lam 2.5. So a value of 2.5 of the behavior factor. So we can just see this and then we close, basically. For the X-lam structure, this value, we have quite a significant scientific research being carried out in order to find the value of the behavior factor. And we found basically that the Q factor of 2, the value of 2, is suitable for X-lam buildings with monolithic walls without vertical joints. While instead, there was an extensive experimental campaign carried out by Professor Ceccotti from CNR, where they tested big buildings in Japan and on a real earthquake, and they found that if the building is made with strict cross-lamp panels connected together with vertical joints, so if they are done in this way, you see, with smaller panels and vertical joints, then a behavior factor Q of equal to 3 can be used. However, if we have a longer panel like this one without the vertical joints, in this case, a behavior factor of 2 should be used. Now, so far, this value of 3 is not being proposed by any regulation. So if you look into the Italian, the current Eurocode 8, actually, the current Eurocode 8, you find only 2, irrespective of the type of X-lam structure. If you look into the Italian regulation now, and you see you find 2.5, which is kind of halfway between the two, without any distinction. So I would say that in the new Eurocode 8 that we are writing right now in European level, we will find 2 for this kind of structure and 3 for the other one. Since this new Eurocode 8 is not yet approved, if you have now to design a building, a cross-lamp building, I think in Italy at least you should be used this value of 2.5 that we find here. So at the moment, the value to be used when you do a design of X-lam is 2.5. Okay, I think we can start here. We can stop here. It's enough for today. And we will have some more consideration about behavior factor and dissipative mechanisms now next week on Monday afternoon. Okay? So thank you for your attention. We'll see you on Monday.